All right. Hello and welcome to Birch Aquarium at Scripps virtual Jeffrey B. Graham Perspectives on Ocean Science lecture series. My name is Caitlin Scully, and I'm excited to welcome you to tonight's talk. Today, we continue with our climate-focused mini-series dedicated to Scripps Institution of Oceanography at UC San Diego's multifaceted work on our changing planet. As many of you know, Scripps oceanography researchers are tackling the tough questions about the impacts of climate change on oceans, ocean ecosystems, and our global society, as well as how science can inform climate change solutions. Tonight, we are delighted to welcome Dr. Sarah Gille for her presentation titled Our Warming Ocean. Sarah is a professor of oceanography at Scripps Institution of Oceanography at UC San Diego. She received her BS from Yale University and her PhD from Massachusetts Institute of Technology and Woods Hole Oceanographics Joint Program. Her work is focused on evaluating the physical oceanographic processes that govern climate, particularly those in the southernmost reaches of the world ocean, where the Pacific, Atlantic, and Indian Oceans converge. She makes use of data collection by satellites and autonomous floats to improve our understanding of how ocean mixing and heat transfer mediate climate warming. Recently, the importance of Sarah's work has been recognized by two prestigious honors. She was elected by her peers as a Fellow of the American Meteorological Society, and she's a winner of the Sverdrup Gold Medal of Excellence in Physical Oceanography. So I'm very excited to welcome Dr. Sarah Gille tonight. Let's welcome her and add her to the stream. Hi, Sarah, how you doing?
Hi. Thanks for the nice introduction.
We're so happy that you're here to chat with us tonight for our virtual perspectives lecture.
Nice to be here.
Yes, and definitely with the climate focus, you are a great person to talk about climate, especially because you've gone on some grand adventures to understand how our world is changing. All right, are you ready to jump in for our first question?
Let's do it.
All right. So over the last decade, we've really seen a lot of high temperatures, a lot of record-breaking years when it comes to warm air temperatures around the globe. Are the same observations taking place in the oceans as well?
Yeah, that's a really good question. The news reports are always telling us about how this year is likely to be the warmest on record. Here's a headline from the New York Times from last February that said January was the warmest January ever this year, and that made 2020 likely to be one of the top 10 hottest years. And a couple months earlier, there'd been a report that 2019 was possibly going to be one of the warmest years on record as a result of El Nino. And in fact, 2019 was judged to be the second warmest year on record. But you can see from this map that's flashing through month by month of the temperature anomalies, temperature relative to average temperature in 2019, that there's a lot of red all over the world. The surface temperatures looked like they were among the warmest on record. And so when we put that together, this gets assembled as data showing long-term temperature change at the surface of the Earth. We as humans live at the bottom of the atmosphere on land. And so when we talk about surface temperatures, we're talking about the part of the world that we live in, the air temperature right where we live. And you can see from this plot is from an annual report that's put together by the Bulletin of the American Meteorological Society that evaluates the state of the climate. It shows surface temperatures from 1900 on to the present, showing this gradual warming so that they've gotten maybe more than a degree warmer over this 120-year period. And it's natural to ask if the ocean is doing the same thing. This is a similar plot. It goes from 1950 up to 2018, showing the warming of sea surface temperature. And it also shows that sea surface temperatures have warmed by maybe a degree Celsius over that time period, almost 2 degrees Fahrenheit. Things get harder when we talk about what's happening below the surface of the ocean. Sea surface temperature is just the skin of the ocean, and we really want to look to dive into the ocean to see how it's changing. When we do that, here we're looking at the changes not in temperature, but in ocean heat content from This is from 1992 up to 2018. And what it shows, so there are a lot of lines here. That's because many different research groups all over the world have done a similar assessment, and they're largely in agreement in showing that the heat content of the ocean in the top 700 meters of the ocean has warmed over this time period. So now, if you're looking at this closely, you're probably wondering what heat content is and what these units are. This is measured in zetajoules. 1 zettajoule is 10 to the 21 joules. But let's put some real numbers on that. If we really looked at this, the total warming over the top 700 meters, that's about a little more than 2,000 feet of ocean. So imagine 2 times the height of the Empire State Building, has warmed up by about 2 degrees Fahrenheit over this time period. And I think if you went and stuck your toe in the ocean, you might not be able to feel a difference of 0.2 of a degree Fahrenheit. That's pretty small, but it's over such a large volume of ocean that it represents an enormous amount of heat. So just to put this in context, the warming of the upper ocean, if you look at this plot, it's about 150 zetajoules over this 25-year period. That's equivalent to a rate of energy input to the ocean of 190 terawatts, which is unbelievably more than 10 times the rate that people on this planet currently use energy. We use about 18 terawatts of energy globally. And that's everybody on the planet, including people who don't have access to electricity and are just burning peat for fuel. So that amount of energy input is equivalent to having every one of the people on this planet, all 7.8 billion people on Earth, running 16 hair dryers continuously over the past 25 years. Now, some of the population of the planet isn't even 25 years old. So all these kids would have had to designate somebody before they were born to start running their 16 hair dryers for us to be using that much energy. It's a phenomenal amount of energy that's going into the ocean and being stored in the ocean. And so, yes, the ocean really warming quite a bit, and over quite steadily over time.
That's really amazing. And considering the fact that there are so many different things that can impact the ocean to cause changes on such massive scales, it really is fascinating to understand and learn how much it's changing over time. Now, Sarah, these are some big things to try to figure out. Can you tell us what are some of the methods that oceanographers use to find out how the ocean is changing in these ways?
Yeah, so traditionally, oceanographers measure the ocean by going to sea. So we go out in ships like the Scripps ship, the Sally Ride, and that takes a whole lot of people going to sea. And we lower instruments over the side of the ship. So typically what you might see is something like this rosette here. So that's a large device. It's actually about the size of a small car, and it gets attached to the winch on the ship and lowered down to the bottom of the ocean. The rosette has bottles all around the sides called Niskin bottles that are used to bring back samples of water. And right at the bottom, you can just about see it, is something called a CTD. It measures conductivity, temperature, and depth. And so it's able to measure the temperature of the ocean from the surface down to the sea floor. But this takes a lot of time and a lot of people. So maybe 4 hours to take a full CTD cast to measure the temperature of the ocean in one spot in the ocean, and days or weeks at sea for perhaps 50 people to collect a whole set of measurements. So that can be a little challenging if we really want to get a lot of measurements. And what that means is that our measurements in the ocean are pretty sparse. This map shows measurements that are available through the database at Scripps for temperature profiles collected in the ocean. This is focused on the Southern Ocean, so it spills out of the Southern Ocean, but this is really showing where there are observations in the Southern Ocean. And these measurements stretch back to 1972. But because they're ship-based data, the ships don't go everywhere, and there are lots of gaps. On top of that, the Southern Ocean is really stormy. It's got really high winds and high waves, and nobody wants to go there in winter. So there are almost no data in winter. And because a ship will go one place but not revisit it, ships aren't very good at sampling what happens week to week, how the ocean changes as a storm passes through, and they don't revisit the same places from one year to the next. So we don't do a very good job of seeing how the ocean changes from year to year. And that's left a lot of gaps in what we understand about the ocean. What's been amazing is the development of robotic systems, what are called Argo floats, to measure the ocean autonomously. So here you see a float going into the ocean, but it's going to be left on its own to make measurements over the coming years. Let me explain a little about how these work. An Argo float is, you can see here this schematic diagram. It's about 110 centimeters high, 3 feet 7 inches, so size of a small child. It weighs about 55 pounds when it's full of batteries. And that makes it something that a single person can haul around and take care of. It's designed to dive down into the ocean to a depth of about 1.25 miles, 2,000 meters. If it goes too deep, to 1.6 miles, 2,600 meters, it'll get crushed under the weight of the ocean. But it's able to make good measurements in the top 2,000 meters of the ocean. And the way it does this is, you can see at the top of this, it's got an antenna on top. And then as you go down through, and it's got a temperature probe next to the antenna. So it's able to measure temperature, a whole lot of circuitry. But then what's really clever about this is it's got a motor and a pump. And it uses a hydraulic pump to change its volume. So it's got a bladder at the bottom, and it can pump a little bit of hydraulic fluid in and out to make the float have a larger or smaller volume. And like that, it can control its density and can control where it is, what depth it's at in the ocean. So with a small amount of pumping, it's able to rise and sink through the ocean. So I'm going to show you quickly a little, if I can, let's go back. I'm going to try and show this video to show how a float gets launched into the ocean. This is going off a container ship. So you can see the float here is wrapped up in a cardboard box to protect it so that it doesn't bang against the side of the ship. The ship's crew has got it lowered down on a cord, and they're going to start lowering it down. This large cardboard box full of the float. And they're lowering it down to the sea. It's a container ship, so it's really high. So it's going to take a while to hit the bottom. It's going down there. It splashes. And now they're going to let it go. So this cardboard box is taped together with some water-soluble tape. So the box is biodegradable. It's going to fall off, and the float is going to be left to go on its way to explore the ocean. So once the float is launched, what does it do? Well, it's on a 10-day cycle. So it's starting at the ocean surface with its antenna. It can transmit its position to satellite. Then it descends down to 1,000 meters depth. And it's going to drift along through the water for about 9 days. So it's just drifting along with the ocean currents well below the ocean surface. And then at the end of 9 days, it goes down another 1,000 meters. So now it's 2 kilometers below the ocean surface. And then once it's reached its bottom depth, it's going to start rising up to the ocean surface. So it comes up and it's able to make a clean profile of temperature and salinity as it rises. When it gets to the surface, it does what anybody would do if you came back into contact with cell phone coverage after 10 days away. It sends a text message and it says, "Here I am, this is what I measured." So it gives us an amazing record of what the ocean is doing, what the temperature and salinity are at that location where it's come up to the surface. So currently, we have close to 4,000 floats in the ocean globally. They cover all latitudes, all longitudes. The floats are, although they were developed at Scripps, they have expanded well beyond Scripps. And the program is about 50% US and 50% international partners. So it's an enormous global collaboration to give us these great global data showing temperature in the ocean, and giving us a really good record of how the ocean is changing.
Those Argo floats are so amazing. And we were talking about before this chat how often people are aware that there are satellites circling the planet, taking readings, helping us with our cell phones, understanding the way our planet is working. But often you don't think about remote objects helping us understand our oceans. So it's so cool that we have the Argo floats out there to help scientists just like you, Sarah.
Yeah, and I think what's maybe not obvious is that satellites are not good at seeing anything below the ocean surface.
Not at all. So these are a really important tool.
You have to send things there directly to make the measurements.
Exactly. And I forgot to tell everybody, just make sure if you have any questions for Sarah or questions about any of the things that we're talking about today, please go ahead and ask them in the comments, whether you're on Facebook or YouTube, we'll be able to see those and Sarah will be able to answer those questions at the end of our presentation today. I know I could sit here and ask you a million questions about Argo floats, but we have to move on. So Sarah, we saw that map, we saw almost 4,000 Argo floats helping us out. Can you tell us what are the floats telling us about how our planet is warming? Is that warming uniform across the globe, or are there regional variations where you might see more or less warming?
Yeah, so Argo is giving us a really great picture of how the ocean is changing. This is a plot showing the global ocean warming from Argo. So this is upper ocean temperature or heat content change just for the period when we've had Argo floats. So it starts in 2006 and goes up to when this study was done in 2014. And you can see the solid line here is showing the warming of the ocean. You can see that there's an annual cycle. The ocean is warmer in summer and colder in winter. It's warmer in southern hemisphere summer. Because there's more ocean in the southern hemisphere. And then you can see that there's a long-term trend in that overall the ocean is warming. But we also can tell from Argo exactly where it's warming. This is showing the patterns of warming trends over the global ocean. And you can see the yellows and oranges here show places that have warmed, greens and blues and purples show places that have cooled. And you can see there are places that are warmer and places that are cooler. So they're different patterns in different places. And it's sort of hard to put all that together, but if we average across lines of latitude, so what we call a zonal average, then you can see that there's really a lot more warming in the southern hemisphere between 20 south and 60 south. And north of that, there's sort of a lot of variability. So we see that there's actually a lot of ocean warming in the Southern Ocean, in the Southern Hemisphere. If we put that together, you can look at the overall trends of how the ocean has changed from 2006 to 2014. Here, there's a black line that shows the average temperature trends from 60 south to 20 south, and it has a really steep warming trend, so showing a lot of warming. And there's a dark blue line that shows the trend in the tropics from 20 south to 20 north, which is really not changing much at all. And then there's a light blue line that shows the trend from 20 north to 60 north, which is showing effectively no change. So we see that over this time period, the time period of this study, effectively all of the warming in the global ocean was happening in the Southern Ocean. And that's a real imperative to try and understand what's going on in the Southern Ocean.
That's really, really amazing. And the Southern Ocean seems like such an exotic place for those of us in the Northern Hemisphere. It seems far, and it seems like an elusive place, at least for me. Now, speaking of the Southern Ocean, can you tell us a little bit more about what is causing the change in that place that seems so far away from us? And are the regional changes forced from what's going on in the atmosphere as a whole, or are they shifts in the ocean? Can you tell us a little bit more about what's going on down there?
Yeah, so this has been a real head scratcher. We wondered when we could see that the Southern Ocean was warming. It's not the whole global ocean. So that leads to a whole bunch of questions. If the whole ocean were warming, we'd have to blame the atmosphere. But if it's just part of the ocean, you could imagine that the ocean was warming because another part of the ocean was getting extra heat So most of the sun's energy comes in the tropics. Maybe the ocean was warming in the tropics and that heat was being transported to the Southern Ocean and stored in the Southern Ocean. So maybe the Southern Ocean warming came from the ocean, but it also was possible that the Southern Ocean warming could come straight from the atmosphere, that the warm atmosphere over the Southern Ocean was very effective at getting its heat into the ocean. And we've also wondered if this goes hand in hand with shifts in the location of the Antarctic circumpolar current or other processes. In the end, I think this Antarctic circumpolar current, that's the major current in the Southern Ocean, doesn't appear to have changed too much, although it's led to a lot of curiosity about whether it could be. But we've really tried to understand whether the changes that we see in the Southern Ocean, this really significant warming, is driven primarily by the ocean or the atmosphere. Now, although Argo floats are great at telling us that the ocean is warming, they don't give us the exact nuanced detail we need to say why it's warming. We really need to be able to dig into the processes. So what we were fortunate to have was a set of climate models run, in this case, by the Canadian Climate Centre, that did a really great job of replicating the observations. So they showed the similar patterns of warming that we saw in the Argo observations and in Argo observations compared with historic data before then. And then we could use that to do an attribution study to try and figure out what the warming came from. So here we're looking at the change in heat content in the Southern Ocean, this black line. So that's what the model says is happening. And then we could look at what was causing it in the model, in the simulations. And what the model showed is that the total air-sea heat flux, the exchange of heat from the atmosphere to the ocean, was the major driver of this. This dashed line here shows the total heat flux, and then all the colored lines show the different contributions to that. So air-sea heat exchange, the atmosphere directly forcing the Southern Ocean, accounts for 75% of the warming we see in the Southern Ocean. And just a quarter of it could be explained by transport that's happening within the ocean. So we really see that the changes in the Southern Ocean are happening because of things that are happening in the atmosphere over the Southern Ocean and how that heat exchange in the Southern Ocean is getting into the ocean. So that's led us to really ask the next questions. How can we understand how the ocean talks to the atmosphere? And that's driving a lot of future research.
Wow. And it's all very important research for us to understand, because even though as I was saying, the Southern Ocean seems so exotic and far, it does have implications for all of us. Can you tell us a little bit more? What does Southern Ocean warming mean for all of us, people here in San Diego to all over the world?
Yeah, so the Southern Ocean is really far away, and it's easy to say, well, why do we need to know about the Southern Ocean? It is so far away that whatever it does to the weather must only affect people who live in the Southern Ocean, and nobody lives in the Southern Ocean. It's all ocean. But the Southern Ocean warming has big impacts, and I'm going to give you a couple examples. One is that a warmer ocean is less effective at storing carbon dioxide. So we know that all of our industrial activity puts carbon dioxide into the atmosphere, and then we try and figure out where this carbon dioxide goes. So a fair amount of it can go into the ocean. It's taken up through photosynthesis and released through photosynthesis, but the ocean is a big sink of carbon dioxide, except that the warmer the ocean is, the less able it is to take up carbon dioxide. So as the ocean warms, we expect it to outgas carbon dioxide and to be a less effective sink of carbon dioxide. So small changes in ocean temperature can have the potential to affect how the distribution of carbon dioxide between the atmosphere, where it acts like a greenhouse gas and warms our planet, and the ocean, where it can be sequestered away and not affect our weather where we live. The other really big example that directly affects us, even if we don't live in the Southern Ocean, is that warming of the ocean affects sea level. So, and that it happens in two different ways. One is that through what's called thermal expansion. Warmer water is less dense. So if you make the ocean warmer, it'll expand and sea level will go up. And that accounts for maybe a third of the sea level rise that we see today. And the second reason is that we're warming the Southern Ocean, and it's next to Antarctica. So as the Southern Ocean's warm water gets into and adjacent to Antarctica, it can go under the Antarctic ice. So the ice shelves that surround Antarctica have water that circulates under them. And that warm water, as it becomes warmer or circulates faster, can be very effective at melting the undersides of ice. It's called basal melting. That, because the ice shelves around Antarctica, they're floating, so they aren't directly affecting sea level, but they act like buttresses or retaining walls to help hold the glaciers, the Antarctic ice sheets on Antarctica. So if the ice shelves are destabilized, that means that it makes it easier for the ice on Antarctica to slide off of Antarctica into the ocean, and that can lead to really monumental sea level rise. So, and that's really a big issue. Here's a photo taken of the Silver Strand south of Coronado, so in San Diego County, at the time of a really big storm. And you can see these waves overtopping the berm and really having the potential to do quite a bit of water damage on all this residential housing on the Silver Strand. A little bit of higher sea level rise, just a few inches more sea level rise means the potential for a lot more inundation, overtopping, and catastrophic effects that really do directly affect people a long way away from Antarctica and the Southern Ocean. So that's a major incentive for us to really try and understand these processes and how rapidly they're happening and what they mean for us.
Wow, that's definitely a lot of impacts that are technical impacts. I mean, people understand the water rising here in San Diego, and we definitely have seen that even right there, as you showed at Silver Strand, but also the fact that the water that sneaks in underneath is really what's helping break off and warm those glaciers. It's kind of crazy to think about.
It is. Yeah, and it's a lot of open science questions, things we're still working to understand.
Yeah, which is why it's so important. You and colleagues at Scripps and around the world are trying to answer these big global questions. It seems to be a recurring theme when we talk about understanding climate is it's not a regionalized thing. It's something we have to understand with climate-wide processes, which can be kind of daunting, but also very cool. Definitely. And so Sarah, along those lines, what drew you to oceanography and this type of science and studying the Southern Ocean with Scripps? How did you end up in this really amazing, cool career?
That's a good question. I could say that some of my earliest memories from being a toddler were being on the beach on the seashore and not wanting to go take a nap. So maybe it was ingrained in me very early on that I wanted to be by the ocean. But I actually grew up in Boulder, Colorado, very far away from the ocean, but with really great access to the natural environment. And that drove me to think really seriously about how to do, I was interested in science, but how to do a science that would have societal impact, and especially in environmental science, where I could do something that had a social good. And so I was drawn to oceanography as a really interesting way to do science, to study the natural world and to better understand what was going on around us. Why study the Southern Ocean? Well, it's an outsized ocean with a really big impact on climate. And it's a really tough place to study. This is a photo from a research cruise that some of my colleagues were on. And you can see that these are really rough conditions for working at sea. The waves are coming over the side of the ship. Everybody's getting soaked. It's a great place to study with a lot of different tools. And I like that. I like being able to use satellite data and autonomous floats and numerical models, all to put together a complete picture of what's going on, to really understand these big scientific challenges. And finally, why study at Scripps? Well, Scripps has tremendous resources. It has ships, it has great engineering facilities, access to the beach and the water. But fundamentally, what Scripps has that I really value is people, graduate students, faculty and researchers, postdocs, academics, amazing staff and volunteers and visitors, over 1,500 people. And so over 1,500 reasons, I think, for me to want to be part of Scripps. I really enjoy being able to work with great colleagues, to learn from my colleagues and students, and to work together to solve some of these really exciting and thorny, complicated problems. So I'm happy to take questions now.
That's really great. Thank you so much, Sarah. And I really appreciate you bringing up how many people working together at Scripps are trying to solve these problems, because I know it's come up a few times in our chat so far, but one of the great things about Scripps Institution of Oceanography and really UC San Diego as a whole is that people aren't doing their science in silos. There's so much intermingling of great minds to try to solve these worldwide conundrums, these questions. So that's really, really great. I'm so glad you brought that up. Now, we do have a lot of questions, and I'll bring a few up. Most of them have to do with Argo floats, and we had a few of what Brandon asked. So Brandon wanted to know, how long do the Argo floats last? And we had another question from Gary along those lines. Part 2 is, what happens when the batteries die?
So those are really good questions. So how long do floats last? Well, we hope that they last about 4 or 5 years of profiling every 10 days. So you can imagine if a float profiles every 10 days, we get 36 profiles a year and a few hundred profiles over the lifetime of a float. So they're really great. They're so independent and they just get on with making measurements by themselves. What happens when they die? That was the second part.
Yeah.
And that's sometimes a mystery. It depends a little whether the batteries eventually fail. We can try to have long-lasting batteries, and some of them do really well, but eventually the batteries can't go on, and the float will start notifying us saying, I think my battery's a little low, and then we never hear from it again.
Aww.
So sometimes they fail at the ocean surface and they might get swept ashore and somebody might pick them up, but probably more often they fail at depth. They're unable to pump, and then they just end up stuck somewhere in the ocean. So eventually they may flood and sink to the sea floor. So we lose them. And what makes them a cost-effective way to measure the ocean is that we don't have to go recover them. So we don't have the ship time associated with having to go pick them up. But it also means that eventually we just lose the floats.
And sometimes that does happen.
Yeah.
A follow-up to this one, I'm just trying to find it in here. I can't quite find the comment, but somebody was asking, do the floats ever just wash up on the beach? Like, they could still be functional, but do they ever wash up on shore? And I had a little bit to add to that too. Do they ever get caught under the sea ice? You were talking about sea ice before.
Those are really good questions. Yeah. So yeah, occasionally a float will get picked up, will get washed up on the beach and show up. Sometimes a fishing boat will pick one up, and because they transmit, it'll send its text messages from wherever it is, some fishing captain's garage, and somebody will be sent to go try and recover it from people. If they come up under ice, so ice in the Arctic and around Antarctica, there's seasonal sea ice. And if a float comes up under the ice, it's got an antenna on top, and it runs the risk of ramming its antenna into the ice, which is not good for the antenna. Mm-hmm. So we have gotten clever over the years, and the floats are now rather paranoid. So they measuring the temperature. If they're in a region that might have sea ice, they measure the temperature pretty seriously as they rise up. And if it looks like it's going to be a little cold and there might be ice, they run away. They go back down. So they will just try and keep profiling, but not come up to the surface and not transmit until the conditions seem more favorable. And then they come up and send all the data they've collected over the past winter. If they do ram an antenna into the ice, then we might lose them.
Oh, man.
Which is sad.
The risk of data. A little 3.5-foot Argo float in the great big ocean, doing very important work.
Yeah.
Oh my goodness. Let's see. We have a lot of great questions coming in. So guys, I think we have time for just maybe one or two more. This is kind of a big picture question from Tom. He wants to know, how is this affecting our oceanic gyres or the big conveyor systems that are impacting the currents around our globe? It's kind of a big,
that's
big
a great question. Yeah. And something we've been oceanographers have been thinking a lot about, because if the whole ocean warmed uniformly, then we might expect that it would have little effect on ocean circulation. Ocean currents depend on gradients in density or temperature. So differences between one place and another. So if everything were the same, there'd be the difference between here and the middle of the Pacific would be the same all the time. It could just get warmer. But when the ocean warming is not uniform, then that will change ocean circulation. And we think that it's probably leading to a speed up of the ocean gyres in some places. The winds are getting stronger, and it looks like the ocean currents are intensifying in some places. In other places, we think the currents, the Southern Ocean, the Antarctic Circumpolar Current, looks like it's moving about the same speed now as it was in the past. But it's gotten warmer, and maybe it's gotten more eddies, more unstable as it's warmed. But this is something we're spending a lot of time thinking about.
Yeah, it's very fascinating. And it also highlights the importance of just understanding basic oceanographic principles of how an ocean gyre works. Because if we don't understand how it works, maybe now or for the last 100 years, it's going to be hard to detect those changes moving into the future as well.
Right. So we need a really good baseline for what's happening now, and we really need to understand the basic physics.
Well, I'm glad you're out there helping figure it out. Definitely very important. So I think our last question is going to be from Patricia, and she wants to know, what can we do to help?
Oh,
I think it's a great, positive, open-ended question there.
Yeah.
Try to make things better.
There's so many things to think about. There are questions about how to help with the research. So there are opportunities sometimes for people to volunteer in research, to get involved in just doing research, become an oceanographer. There are opportunities to help fund research, donate. There are opportunities to help think about how to move forward in addressing global warming, reduce greenhouse gas emissions, think about mitigating climate change, less air travel. We've mostly been pretty good at that this year.
Whether we want to or not.
And thinking about implementing more renewable energy. So there's a way for everybody to help, and something that will meet everybody's desires for how they want to participate and do something.
Definitely. And I think looking to the future is if we're trying to be climate minded as we make decisions in our day-to-day lives. It doesn't always have to be huge things, but working together, we're all hoping that we can make a difference moving forward. So thank you, Sarah, so much for this great chat. And thank you to everyone who submitted their questions. This will live on if you'd like to share it with any of your friends on our YouTube page, so you're able to watch it there. And so we're going to say goodbye to Sarah right now. Thank you so much. We're all going to give you
so much. Thanks for the great questions.
Yeah. And thank you for being with us, Sarah. And I'm going to go ahead and tell you guys a little bit more about our next lecture coming up. We have another lecture with Van Ramanathan coming up next month, and I hope you guys will tune in. You can find more information about it on our Facebook page. And then also, I just wanted to take a moment to see if anyone out there felt like they were able to support Birch Aquarium at Scripps. Before we totally wrap up, I really want to thank everyone who has supported Birch Aquarium through our temporary closure. We are still currently closed, but those of you who have supported Birch Aquarium, thank you. You've ensured that important educational programs like this lecture series and our virtual summer camps have been able to continue on while our doors are temporarily closed. But you've also helped to feed the more than 6,000 creatures that call Birch Aquarium home, including our little Pacific lumpsuckers, which is our staff favorite. I feel like our sea turtle gets a lot of love, and we love her so much, but we can't forget those little guys as well. And as I said, though our doors are temporarily closed, we're proud to be a resource for our community and thankful to all of you who support us, because it's really you who make it possible. And if you're able to, please go ahead and make a gift at aquarium.ucsd.edu/give. And that will help ensure that all of the great programs, our role in the community, will be here for people into the future. So thank you so much, everyone. And thank you for tuning in today. I'm looking forward to chatting with you all next week. Have a great rest of your evening.